We can go ahead and get started. So thank you so much, everyone, for coming to the LPI virtual seminar this week. It's my great pleasure to introduce Dr. Jim Bell as our guest this week. Dr. Bell is a professor in the School of Earth and Space Exploration at Arizona State University. He is also an active planetary scientist involved in a number of planetary missions, including Spirit, Opportunity, Curiosity, of course, Perseverance, the Mars Reconnaissance Orbiter, the Lunar Reconnaissance Orbiter, and go on from there. And he's also the past president of the Planetary Society, which is the world's largest public space education and advocacy organization. So it is my great pleasure to have him here to talk with us today, where he'll be talking about the early exploits of the Mars 2020 Perseverance rover. Thank you so much, Jim. Take it away. Oh,
great, thanks, Ryan.
Sorry, before I begin, make sure everybody that your mics are muted during the talk. If you have a question for Dr. Bell, please go ahead and feel free to put it in the chat, and then I will read those off at the end of the talk. And you can also request it to unmute your mic, and then we can, if you wish to ask a question of them directly. Take it away, Jim.
All right, thanks, Sean. Appreciate it, and thanks to the LPI for inviting me to participate in your colloquium series. And of course, I wish we could be together, but this will have to do. Also, special thanks to fine ASU graduate Project Imane for talking me into this and twisting my arm, and I'm glad you did. And you guys are lucky to be working with her. She's awesome. So I'd love to give sort of an update on what's been going on with Perseverance since we landed back in February. I'm the principal investigator of one of the science instruments on the rover, the Mastcam-Z, mast camera zoom system, stereo multi-spectral imaging system. And I'll mostly focus on the initial observations that we've been taking with the Mastcam-Zs. But I'll talk about some of the other things that we're doing and give, let's see if I can get there we go. Give kind of an overall reminder of the mission objectives and the specific goals of just the observations and what we're doing in this first 90 sol on Mars period. Some examples of these early observations, and near the end I'll just provide a summary, and along the way a summary of sort of publicly and community available resources for folks who want to follow along. We take very seriously the idea that we want the public as well as our professional colleagues to be able to follow along with what we're doing and seeing and experiencing. A little icon with the 3D glasses is to warn you in advance, in case you have some lying around, that there will be a few 3D slides in this presentation. So if you've got some handy, you might want to grab them. Yeah, so let's jump in. And a lot of this might be reminders to folks. There's sort of 4 major, pretty ambitious overall goals of the Mars 2020 mission that are all related to understanding the possibilities for past, present, future life on Mars. 4 primary science objectives related to geology, astrobiology, sample caching, and preparation for human exploration. On the geology side, very similar kinds of high-level objectives that have been the case for previous Mars landers and rovers and other planetary landed kinds of missions, right? Looking at the scale of the context and scale of the geology, geomorphology, landscape evolution processes, trying to get at the origin and evolution of the landforms that we see from the orbital scale, getting that sort of meter scale that we can measure from orbit with tools like HiRISE, down to the micron scale, tens of micron scale capabilities on some of the imaging on this particular landed vehicle. And so this gets at the context for the eventual sampling that we'll do, and the study of geologic processes at all of these scales. The astrobiology goal is really driven by the choice of landing site. Many of you may have participated in the multi-year-long process of selecting Jezero crater as the landing site, as one of the places that the community and the team believes has among the highest probabilities of harboring evidence of past life, or perhaps even present life in the subsurface Not to say that there's going to be life there, that we will find that evidence, but it's all about maximizing probabilities, and I'll come back to that in a moment. Major objective of the mission is to collect samples. This really, when the mission was formulated, science definition team back in 2011 and 2012, it was pretty much a community consensus that, it's great to send another rover there, but not just on its own. It must be part of a Mars sample return effort. Of course, this is consistent with the last decadal survey, the one we're still operating under until the next one comes out, begin the process of Mars sample return. And so Perseverance and the 2020 mission are the first part of that process. So collecting samples is critical to mission success. None of us on the team, I think none of us on the team, believe that the mission will be complete and successful until those samples come back. Of course, lots of fans of samples and sample analysis at LPI, JSC, and other parts of this community. So we collect them on board, up to 30 or 40 of them, and store them on board, and then decide to depot them in some way that's still to be determined, depending upon what the terrain offers us, and depending upon what is coming next, the planning for the rest of Mars sample return, fetch rover, lander, orbiter, etc. Of course, many of you know all that is being actively planned. Speaking of actively planned, a major goal is to prepare for human exploration. Several experiments, including an oxygen generator on board, designed to demonstrate future technologies, and also just the active study of the current meteorology, the dust cycle, the water cycle, the climatology, the modern meteorology of the environment will be important for future human exploration as well. So that's an important part of our mission. High level timeline, that Jezero was selected as a landing site at the end of a multi-year process in late 2018. The rover actually started getting designed and built back in 2012, 2013, all the way up through launch. It was being tweaked, including its software, which is being tweaked after landing even. So it's a continual process. One of the reasons that this rover exists at all is because it's made from something like 90% spare parts from Curiosity. So an enormous amount of heritage in many of the systems that Perseverance has come directly from the Curiosity experience. And of course, Curiosity is still going strong, doing amazing things in Gale Crater. And we continue to learn things from that mission. Actually, it's a two-way street, so that's been exciting. Rover was launched in late July last year. Heroics from up and down NASA, JPL, supporting aerospace contractors, the team at KSC, just to get the rover, through ATLO, out of JPL, from Southern California to Florida, into its final configuration, into the launch vehicle, to get the launch vehicle prepared, and all that during a global pandemic, with no major debilitating events or harm to the team. So that's pretty incredible. Just hats off to that group. And then we cruised from late July to early this year, landed on February 18, 2021, and we've been doing surface ops since that time. And at 1 o'clock Pacific, 3 o'clock Central, we're 15 minutes into Sol 96 of our mission. Nominal mission, prime mission, a Mars year, so a little more than 2 Earth years. And then we'll, of course, see what things are going and what we might be able to do after that. Landing site selected in Jezero crater, right near the boundary between Syrtis Major and Isidis, Planitia. You can see, I just made this chart yesterday, first time, all 10 landing sites, including the Chinese Zhurong lander and rover, all 10 successful operational landing sites on Mars here. And so Perseverance has a little bit of a crowd in its area, but the main target was Jezero crater, this 40-50 kilometer diameter crater that hosts 2 spectacular fan delta deposits, and the main target for the landing is the western delta deposit. number of orbital studies using MRO and Odyssey and Mars Express and other data sets, have studied the geomorphology, the mineralogy, details of this particular place, and it's the fact that it is a beautifully preserved but ancient delta was one of the main reasons that it was quickly made the top of the list among the choices of places to land. Lots of community debate about that, of course, but ultimately it was judged to be a very high priority and to be among those places on Mars that could maximize the probability of addressing that habitability question, that life on Mars question. So a number of studies are most recently reviewed by Katie Stack and a bunch of folks from the team, actually, in the Space Science Reviews paper referenced there. A number of studies in community looking at the geology, the geomorphology, the mineralogy from instruments like CRISM on MRO, from instruments like HiRISE on MRO, HRSC on Mars Express, et cetera, used to characterize, long before we got there, the basic regolith and bedrock units that we believe that we would encounter with the vehicle. So a number of these units have been defined. I'll point out two things. When we landed ultimately at B prime here, which is interesting, and then I'll just keep this little dot in mind there. That little dot is an outlier of the delta, and it's actually the one on my screen background called Kodiak, and we'll see it in more detail from the surface in a moment. Also outlined in that Stack et al. Paper is a series of hypotheses, hypothetical scenarios for the origin and subsequent alteration, evolution, landscape evolution of the units, primarily the bedrock units that we see from orbit in Jezero crater. And 4 primary scenarios are presented in that paper. I won't go into them in too much detail here, but you can see from the cartoonish strat columns here that the age of the delta relative to the cratered floor, the fractured crater floor, the CF units, varies depending upon these scenarios. In one scenario, the crater floor is the youngest unit and embays the deltaic deposits. In several other scenarios, the delta is the youngest unit, and the crater floor materials, which might be volcanic, which might be lacustrine, based on orbital observations, the relationship is opposite. They are older. So all of these scenarios, as outlined in that paper, produce multiple working hypotheses, which we believe can be addressed with observations from the ground. Observations with the kind of instruments and systems that we brought with the Perseverance rover. Of course, working in collaboration with in some cases, continuing observations from orbital platforms as well. So multiple working hypotheses, testable hypotheses are guiding our choice of, guided our choice of landing site at all, and now it's guiding our choice of traverse paths, and I'll come back to that in a little bit. So how do we address those hypotheses? There's a competitively selected science payload that's on the rover that ranges from imaging to ground penetrating radar, spectroscopy, variety of ultraviolet, visible, near infrared spectroscopic techniques, laser ablation for elemental composition, PIXI kind of instrument called Pixel for elemental composition at a very, very small scale, fluorescence, Raman, so a pretty impressive arsenal of instruments to throw at those hypotheses and to help use as triage, basically, to select samples. We think of the cameras, for example, as a major triage tool. Where do we take the vehicle? Where do we choose to sample? What regolith deposits, outcrop deposits? And how do we assess and document the context of those samples, which will be critical in their assessment when they eventually come back to the laboratories on the Earth. They cannot be analyzed in a vacuum. Maybe some instruments will require a vacuum, I guess, but they can't be analyzed without understanding that context and their relationship to each other. And that context guides our choice of them in the first place. We can't sample everything that we see, so we have to use this payload and the capabilities of the vehicle to sample as intelligently as we can. I'm a camera guy. There's tons of cameras. This is the most camera-rich spacecraft ever sent out into deep space, at least robotically. And you know, you can see some examples of them here. There, if you count all of the cameras, including the ones that were on the back shell, the parachute, all the amazing movies that you hopefully have seen of the landing process, something like 25 cameras overall, including several on the helicopter, the Ingenuity helicopter, another tech demo experiment designed to feed forward to future robotic and human exploration, not just on Mars, but you know, Titan and elsewhere, being carried by the rover. So very, very imaging rich investigation with the vehicle, and we've been exploiting that. And the sort of small armada of orbiters around Mars are providing us with lots and lots of downlink compared to previous missions. We've been very fortunate to have the ability to link up with the orbiters at higher bandwidths than previous vehicles, and thus get much more data back down to the Earth. And most of that much more data is imaging data, including some cool videos and things that I'll show you here in a bit. Okay, so February 18th, we landed successfully in Jezero crater. You can see the crater there and the landing ellipse, and there's the location of the landing. And you can go to this website, by the way, hosted by NASA, and see where the rover is at any given day. I'll just zoom in a little bit here. So we landed a little bit outside, but well within the 1 sigma range of the landing ellipse. If you've seen those movies of the landing, you have seen the divert maneuver and the fact that the active terrain navigation was active. The rover the vehicle was heading for relatively large obstacles. It steered it away, and specifically in this, I don't know if can somebody confirm you can see my cursor?
Yes, we can.
Yes, okay, great, thanks. So specifically in this area here, lots of big sand dunes and some rugged terrain. And that's where the vehicle was heading, because it's much closer to the center of the ellipse, and it diverted itself away. So we actually landed a little farther from the delta, the scarp of the delta, than we would have otherwise, but not in an area that has since proven would have been untraversable, especially because of the big sand dunes. So that was successful demonstration of that technology, which can be used for future Mars or other landed missions. We'll zoom in here to a little closer up view of where we are. And here's that very sandy and rugged area that I was mentioning here. Here's that little dot called Kodiak that I was talking about earlier. And here's the front of the delta. So we ended up something like 2.5 or so kilometers from the front scarp of the delta. So good news, bad news. We would have been maybe better to land right here. It wasn't an option given the way the winds were blowing the vehicle and all that. But the algorithm took us to the safest spot that it could find, and it turned out to be a good spot to land, which is great. Zoom in a little bit more. And here's what we've been doing since February. Driving around, but not a lot, right? You can see the total drive distance is under 400 meters. Part of the reason is we've been characterizing and demonstrating the capabilities of the mobility system. Demonstrating that we could drive at all in the first case was part of this early period of the mission, called the surface operations transition phase. We were in the cruise phase to get to Mars, and then landing, entry, descent, landing, and then surface operations transition, or SOX phase, was always expected to last somewhere between 60 and 100 salts. It's going to end up being just about 100. So there was our landing site. You can see at this scale in the high-rise data here, you can see some of those scary sand dunes off to the west, but also some really interesting polygonal terrain off to the east and around us, lighter toned, fractured, some pretty long continuous fractures running through this unit. We are on a crater floor after all. And you can see the drive path that we've taken, kind of circling, looping around. The blue hatched area is the helicopter airfield. So one of the other goals of this early period of the mission is to support the helicopters, the Ingenuity helicopters tech demo mission of about 30 of those 60 to 100 sols on Mars. And so we were able to do that successfully. Helicopter is kind of on its own now, doing another tech operations demo phase, but without the kind of rover support that and highest priority that it was given for that 30 sol period of the mission. But that's the nominal airfield area for the helicopter's first flights. And we've been, we had to find a place to park, to watch the helicopter flights and to be stationary with the helicopter's little antenna on the rover pointed at the within clear line of sight vision of the helicopter for best communication. So that was a constraint. So we had to remain parked. We used that period of time to take a gigantic panorama at high resolution, which was a good use of our time surveying the landscape. And now we're starting, you can see, we're starting to head towards the east a little bit and to the south. And we're about to finish this SOX phase of the mission and begin a real science campaign. And I'll come back to that at the end. Here's what that place that we landed at looks like from the surface. One of the first things that we did, pop the mast up on the rover and take a relatively low resolution panorama with the navigation cameras, and then a higher resolution, about 3 times higher resolution panorama with the Mastcam-Z system on the rover's mast, 360 degrees. Just get the lay of the land. You see these beautiful scour marks from the retro rockets as they scoured these rocks and regolith materials on the surface. This is almost at our lowest resolution for Mastcam-Z, so it's relatively smaller number of images, relatively lower and quicker downlink to get it back to the Earth. And it also allowed us to build our first, since we did left and right images, our first stereo products and start to look at the topography and the detailed lay of the land. I'm not going to go into all of this in great detail, but if you're able to access this presentation later, you could go back through it if you'd like. But just some of the highlights, early mission observations and achievements. Really, the first week or two of the mission was just all about settling in, turning instruments on, testing mechanisms, making sure that antennas, high gain antenna worked properly, the wheels would wiggle and spin properly, that the camera zoom and focus mechanisms and filter wheel works properly. All the other instruments have a variety of other mechanisms that are getting tested out, making sure we can point the mast properly. It takes days of ground in the loop to get the telemetry and the confirmation that all of this works. That first week or so, we were still on the cruise flight software, so it wasn't until between Sol 5 and 8 that we uploaded new software to the rover that had been getting developed and tested in the test bed during the cruise, right? Typical of these kinds of projects, lots of pressure to get to the launch pad. You're not going to be able to finish everything. So a lot of the development was done and tested on the testbed rover at JPL, and the software uploaded early in the mission. And so since Sol 9, we've been on the nominal surface science mode software, and still spending much of the time doing the instrument characterization, test, calibration, especially of the spectrometers and of the multi-spectral capability of cameras like Mastcam-Z, imaging of our calibration targets before they start getting too dusty. The SuperCam instrument, which uses libs to get elemental composition, has a big array of calibration targets, well-known standard compositional materials. I'll show you a picture of it in a moment. You've probably seen it. They're systematically going through those and verifying that they're getting the spectral resolution, signal noise performance, and all that. Just an enormous amount of, this is why it's the transition phase of the mission. It's really about calibration and characterization, trying to sneak in as much science as we can during this early time, acknowledging that we're not really in exactly the place we want to be. We want to get over to those delta deposits or the delta remnant deposits. That's our primary objective. So we're not exactly in the best place that we think, but it's an interesting place. We want to characterize it, and I'll come back to this at the end. We want to sample it as well. And so it is to our benefit to do the surveys that we can do during this early time with the remote sensing instruments, with the NavCams, the hazard avoidance cameras, with the Mastcam-Zs, with the high resolution telescopic capability of the SuperCam remote imager. So that's been a major part of what we've been doing these first few months. Another major part, as I mentioned, those supporting those helicopter flights. I'll show you some results from that, both the video support, basic imaging support, video support, and audio support of the helicopter, which is kind of cool. Of course, the SuperCam instrument and the entry, descent, and landing system on Perseverance have carried the first microphones to the surface of Mars, and they're both working beautifully and sending back sounds of the vehicle and sounds of the environment. Since that dedicated helicopter flight phase has ended, we're continuing to do instrument calibrations and checkouts, continue to do surveys of the landing site and environs, and I'll show you some of those results. Around Sol 100, which is Tuesday, coming up, sometime between now and then, there'll be someone will wave their hands and say, okay, SOX is over, now it's time for our first science campaign. And we've sort of mapped that out, got a plan for that. And we think that enough, but not all, of the rover's capabilities are online to get us going on a really good science campaign on this crater floor unit. So I'll talk about that. Since I'm in charge of Mastcam-Z and we run our team out of ASU and Malin Space Science Systems, I just couldn't resist showing off some hardware. These are just great cameras to work with, very much like the Mastcam system on Curiosity, except those are fixed focal length, one wide angle, one narrow angle. The Mastcam-Zs are matched focal length, so we can get stereo at wide angle, we can get stereo all the way at telephoto, about 110 millimeter lens telephoto. And so we've been doing a lot of work at both extremes and various points in between, depending upon how much coverage we need, whether we want high-res stereo, low-res stereo, what kind of bandwidth we have available, how quickly we need the data down. We can compress the data, we can not compress the data, etc. So I point you to the instrument paper and the calibration papers. In that, there's a special issue of Space Science Reviews that describes the entire payload and the mission and the landing site for the mission series of papers that came out last year. So check those out for more details. We're doing both science imaging and operations support imaging. I think it's important to point that out, that we want to be able to use the high-res capabilities of the science cameras to help the rover drivers drive farther into stereo mesh, to help the arm placement engineers put the arm down more accurately into the workspace, to provide context for other instruments, taking especially the spectrometers, many of which can just look at tiny points or really centimeter scale pieces of the ground that the turret places them on. And so giving the context imaging is a kind of a support that we do for those investigations as well. I won't read all these again, but I'll show you some examples of what we've been doing with these cameras since the beginning of the mission, since our first 360, which I showed you at low resolution. We've augmented that now with a full 360 at our maximum resolution from an area close by. Still pretty much the same region. You saw that we haven't traveled very far yet from the landing site. Doing that, could you mute your phone, please? Or mute your call, please? Thanks. I talked about supporting the Ingenuity flights. I'll show some examples of that, and I'll show some examples of some of these high-resolution rock and regolith surveys, and finally our multi-spectral work. We're still working on getting our calibration in place and making sure that we're getting the right kinds of data to understand the reflectance properties of the surface, but we're off to a really good start. So I'll show you some examples of that as well. In fact, here's some early images from just 2 days after the second day after landing of our calibration target. And here's that SuperCam calibration target I was mentioning with its many, many elemental and mineralogic standards, including a SNCC meteorite that's on here as well, piece of a SNCC, return to sender, right? So taking these kinds of observations of these calibration targets before they start to get really dusty, which they will over time based on MER and MSL experience, is pretty important. You can see, in fact, that our cal targets they have these very strong magnets around the circular regions here, and these are provided by, the CalTargets were built by and provided by colleagues at the University of Copenhagen, and it's designed to catch magnetic dust. And it started doing that during the landing event. You've seen maybe the movies of the dust cloud that was created during landing, and a lot of that material and the dust of Mars itself is highly magnetic and was captured by the CalTarget magnets. So we're able to, well, as that material builds up, we'll be able to eventually characterize it with Mastcam-Z and with the SuperCam passive spectroscopy as well. So that's pretty exciting. It's an example of our resolution capability, highest resolution, closest point to the rover. We can resolve sort of millimeter-sized grains with the mast cameras. And then of course, there's a camera on the arm of the rover that's called Watson. It's very much like the Molly camera on Curiosity. It can go down to the surface and pick up that millimeter scale and take it down to the hundreds of micron scale. And then inside the Sherlock camera, there's another imager that goes down onto the surface and gets down to the tens of micron scale. So, you know, going from orbital meters to millimeters from the mast to microns from the turret mounted instruments, the arm mounted instruments, again, getting at the scale, the variety of scales and processes that I talked about earlier. I actually forgot to bring my 3D glasses to my desk here, but if you happen to have some 3D glasses and you want to see examples of some of our stereo images, here's a couple of relatively early ones. Our big panoramas are in stereo as well. I'll point out, I'll mention now, you know, we put all of the images out there every day in raw form, and there's a whole bevy of amateurs who are amazing image processing experts, and they're creating beautiful panoramas and stereo images and VR, Oculus models. It's really amazing what they're doing. We're doing a bunch of that, of course, within the team as well, not just for joyriding and fun, although it is, but really to help us understand the context and the placement of instrumentation, the drive decisions and obstacle avoidance or obstacle desirements in terms of some of the high standing rocks using that stereo capability. Excuse me. I showed that early panorama full screen, or just taking up the full screen, and every frame of that you can zoom in and see this kind of resolution. So it really is, these are panoramas you can get lost in very easily, just enormous amounts of detail in the landscape. And so of course the team is diving into that to start thinking about initial scientific analysis, surveying the rock populations, looking at regolith properties, etc. Then I know also the public is having a lot of fun with them as well. We very quickly realized that there are maybe just a small number of classes, sort of morphotypes, morphometric, morphologic classes of rocks right where we landed, a couple of kilometers away from the delta, presumably in a part of the crater that was where the lake was relatively deep, as moving distally away from the deltaic deposits. We see these sort of lighter toned, relatively flat-lying paver kind of rocks that make up the polygons that we saw from orbit. We see another population of darker toned, very associated, similarly textured but darker kinds of rocks associated with them. And then we see a whole bunch of much higher standing, some of them maybe outcrop, some of them definitely float kinds of rocks around us, especially to the east of us, where it's a much more rocky terrain, where the landing system avoided that area for us as well. I'll show some images of that. But relatively small number of types of morphologic types of rocks that we're seeing. An interesting subclass of the typically higher standing rocks are these sort of wholly pitted textures that we typically see in light toned rocks, but we also see them in some dark toned rocks as well. Are these vesicles? Are these from frothy volcanic lavas? Are these ventifacts, flutes and ventifacts created by billions of years of aeolian abrasion? Are they sockets created by the dissolution of mineral clasts in a matrix, a breccia or some other kind of matrix? Are they all of the above? Are they none of the above? Are they something else? You know, I wish I could sit here and tell you the answer. There's a lot of mystery to these, because just when we think we might have it cornered, we'll turn a corner and see other examples in these big panoramas and mosaics that kind of fly in the face of a simple explanation. So surprise, surprise, Mars is surprising us. And so I can report that the team is working hard to try to collect good observations, the best observations of the diversity of the population of these and the other morphotypes that we're finding at the landing site. The folks who are involved in the compositional side, the LIBS folks, are targeting a number of these rocks, still working out a lot of details of their calibration, but trying to look at their basic composition, trying to infer what we can about mineralogy at this point without being able to sample, abrade, clean off the dust yet. Those systems not online yet for the vehicle. So we're a little bit at the mercy of the primarily remote sensing instruments that we have available right now. And so it's only part of the whole toolkit. We expect to continue to see many of these kinds of rocks along our continuing traverse as the full capabilities of the rover start to come online. So that's going to be much more beneficial for our interpretation. I guess I could have been showing this cool 3D movie while I was giving that little speech. This is just an example of the kinds of fly through and flyovers at the few millimeters per pixel scale that we can do with our 3D imaging. In this case, it's that area around one of those scour marks, the area that was where the retro rocks were helping to slow the vehicle while it was lowered down, and stop the vehicle while it was lowered down the sky crane cables. So it's great to be able to use these for both scientific and public outreach purposes, of course. I mentioned that we have more recently, starting very early in the mission, get some examples of our highest resolution imaging capability. First, we shot just along the horizon, especially focusing on the delta scarp, which I said, a couple of 2.5 kilometers away. And these images were where we started seeing our first evidence of the layering. You could see from obviously horizontal orientation. You can see some evidence of that layering in high-rise data. Of course, it's part of the typical, the interpretation has led to this being interpreted as a typical deltaic succession. But now being able to see them from the ground and seeing some of the places and starting to think about what are the best places along the delta scarp where we'll have the best exposures. Because we're going to be driving over there eventually. We'll be getting much closer to these exposures. You can see there's a lot of, I'll show some examples here, individual examples of some of the pieces of the delta scarp and some of the outliers. There's a lot of scree here, right? There's a lot of just regolith that's been flowing downhill, probably burying the exposure of many of the fine grain, the finely layered materials. And so, some of these are probably not the best places to drive over and expect to be able to get the rover into position to either do up close in situ or close remote sensing observations, or even sampling of this kind of material. So again, triage for the science and the interpretation of what we're seeing, as well as the eventual traverse decisions about how and where we will get over to these delta deposits. Some of the indications from this distance are really compelling, right? And there's, maybe these are inclined foreset beds that we'd expect to see at as part of a typical distal deltaic sequence, impinging at low energies into a shallow lacustrine environment. Or maybe these are erosional slumps. Maybe these are flat-lying layers and they've slumped down. We need to see lots more examples of them. And to that end, we have just completed acquiring that full resolution. You can see some rover parts there, and pretty soon you'll see there's an alien spacecraft in the view there. We'll come back to that. But we have just recently finished acquiring this full resolution Mastcam-Z, full 360 from the horizon all the way down to the rover, nearly 1,000 different pointings, 1,000 images per eye almost to go into this product. So every part of this scenery, you can zoom in by like a factor of 10 and look at these individual rocks, and it's just it's a candy store of rock and regolith morphologies and characteristics. And so we're using this information, and we're just about to get a public release version at full resolution and lower resolution. The full resolution PNG file is something like 2.5 gigabytes. So we're also going to offer in lower resolution for people who can't handle that. That should be coming out hopefully sometime in the next week or so. But playing with it among the team as well, using these kinds of measurements to characterize what we see in the delta, as well as just the general properties of the rocks and regolith around us. Part of that mosaic includes this beautiful Kodiak feature behind me, more sort of false color, a little more garish behind me, a little less Andy Warhol in the version on the screen here. Part of the challenge has been timing the exposures, the time of the exposures to get the right sunlight on these vertically illuminated surfaces. The first time we shot Kodiak, these spectacular layers and cross beds were in shadow. We could barely see them. So instead of afternoon, we're looking to the west. We wait till we instead do early morning. The sun is relatively low from the east, and it illuminates these much more normally. So figuring out the timing of all that kind of imaging, which of course varies with azimuth for these features, has been a part of what the planning process and part of the strategy for acquiring images of these kinds of features. So you could see some beautiful truncated cross bedding. Lots of debate going on in the team on the potential aeolian versus fluvio-lacustrine and then deltaic origin of these features. We've got a number of views like this now that you can see for yourselves in the raw data released to the public of the other deltaic remnants at optimal lighting. And we're able to zoom in on these just a little bit more with the SuperCam instrument and get even higher fidelity, higher resolution views of some of the details of the layering, the cross-cutting relationships, the contact relationships in the layering, and the presence of clasts, boulders, other structures that we see in and among these layers. So that's been an important part of the evolving hypothesis testing for what we see. Are these in fact deltaic remnants, or are they just erosional remnants from just more erosionally resistant material that happens to have been aeolian, involving large-scale aeolian deposition, large-scale sand dune that has been lithified. So we can test those hypotheses with just a little higher resolution view of some of those layers and relationships. So that's been a lot of fun and interesting, and lots of great debate going on inside the team about what that means and how those can be interpreted and what additional tests we can do. Here's an area that we scouted in the early Sol 20s because we had to park the rover not too far from the helicopter, and we wanted to park it in a place where we knew we were going to spend about a month, but we could use the arm and deploy the microscope and the SuperCam LIBS instrument on rocks in a work volume. So we used these kinds of images again as triage, as scouting tools, and we ended up parking in a pretty interesting place where we could do a lot of that work. Meanwhile, we're supporting the helicopter, and I think many of you have probably seen many of these movies, but in mid-April, sort of for the first time, flying an air-powered vehicle, a powered vehicle on another world. Pretty exciting. Lots of coordination and choreography between the rover team, the camera team, and the helicopter team. Here's its historic first flight. See it battling the wind there a little bit. We were about 70 meters away. They just wanted to, just for safety, you saw it do a little maneuver there. See the wind kind of pushing on it a little bit. It's fighting back. Lots of great information on the boundary layer here coming from the helicopter telemetry, and then gently settling down onto the surface. And that was, we had practiced that a number of times. We had maybe 3-4 weeks of effort on the imaging team to do that coordination. So that was pretty cool. The helicopter ended up flying 5 times. Here's another view of that process by Mark Lemon on our team with a filtering method that removes sort of the average, and you can see how much dust was lifted by the helicopter. If you watch in either of the right-hand frames, as it takes off, by enhancing the view and ratioing to the average, you can really, the dust really comes out. You can see it in the original frame at upper left without any enhancement, just much, much harder to see. So this has been used as a science experiment about dust properties and the properties of the lowest boundary layer, wind speeds, vortices, wind directions, all that kind of stuff. It's been kind of an unanticipated atmospheric science experiment coming out of this. Let's see, is this the fourth flight that we captured? Yeah. So this one has sound. I don't know if you'll hear the sound. Hopefully you have listened to the sound of the wind. And then the helicopter starts speeding up. If you can't hear it, let me know. It's a low hum. Hopefully you can hear it. Anybody hear it?
Yes, we can hear it.
Okay. That was pretty cool too, you know, and we had to coordinate that and choreograph that with another instrument to be able to capture the sound. We could still hear it. It went off screen. We were not able to follow it. We're not allowed to move the mast because electrical interference of the mast interferes with the communications with the helicopter. So bummer, we would have been able to follow it. That would have been great. Couldn't do it, but you could still hear it when it's like 100 meters away. And this was totally defied the predictions of how sound waves travel in the atmosphere of Mars. So there's some real interesting audio science that's going to come out of this, and atmospheric properties science come out of this. You can hear it getting a little bit louder now as it's coming back a little bit closer. And the wind is also gusting occasionally and dying down. How close are we? Yeah, we're getting close to, whoops. Let me bring it back. Here we go. And you can even hear the motor powered down at the end if you listen really carefully. Powered down. So that was also just a really exciting experiment. Of course, supporting the tech demo is the main goal, but there's atmospheric dust and atmospheric pressure science coming out of this as well. And of course, the helicopter is taking its own images along the way with its cameras, mapping the area. This was all area that we knew pretty well because we'd driven the rover over it. But now, after those first 5 flights, it's now in this and its own sort of operations mission. It's flown once on its own without any rover imaging or other support now, and it's taken a whole bunch of pictures in the area where we can't go. It's going to continue to do that, surveying places where we can't take the rover, either because it's too untraversable, sand, rocks, whatever, or it's just out of the way. It's just we don't have enough time. We're on a path to try to get to the Delta by a certain date, maybe around Sol 300 or so, and we don't have time to go everywhere. So the helicopter is going to try to prove out that capability for us. So that's exciting. Here's another view of that takeoff, and again in the enhanced dust mode. So as the helicopter took off, it lifted dust again, and you're going to see now when it came back, when it comes. Okay, here it is going off out of the field, goes and does its hover, comes back, and look at how much dust it brings when it comes back. I think this is so cool. This is kind of unexpected. It had flown over this area previously by the time of this flight. So a lot of the dust that could easily be lifted had been lifted, but where it went way off to the left, it hadn't flown before. So it must have entrained a bunch of dust in its chopper wash, and it brought it back. And you can see that cloud of dust as it's coming back in. So again, the rate that dissipates, the direction it moves and all that, the atmospheric science folks on the team are having a field day playing with that. And then the final flight that we recorded, the 5th flight of the the helicopter's prime mission, we didn't record the liftoff, but we recorded the landing and where it was supposed to go. It flew at about 5 meters, went up to a 10-meter altitude. Again, now it's taking pictures to build stereo meshes of the surface, and then landed. And so we caught that. Also with audio, I don't think I put the audio in this one, but there's a version on the website, the NASA website. Wide angle with this camera, and we have 2 cameras, and so we caught the landing at narrow angle. And you can see it stick the landing there. And just because we can, because that was extra high frame rate, we can see it again in super slow-mo. So that was, I think, just really successful, and lots of satisfaction from the operations planning folks on our team, and great coordination with the helicopter team and with the rest of the rover team supporting that very successful tech demo mission of the first drone on another planet. Pretty exciting. Okay, so I mentioned that we've got color capability, and we can use that in garish ways to enhance the color, to bring out, try to use color variation at red, green, blue, as in this case. This is a decorrelation stretch of just red, green, blue, super exaggerates subtle color differences. We can see that there are, again, just a couple of classes, rock color classes at visible wavelengths. Some of them are dusty. There's a couple of classes of regolith materials that you can see in pretty harsh, exaggerated color stretches like this. So we were able to pick those out. And we use these, again, as a triaging tool. Where should we park to sample the maximum color diversity? And maybe color diversity means chemical diversity. Maybe it means mineralogic diversity. Maybe it just means textural diversity or grain size diversity, that you can't unconfound all of those effects, but we can maximize our ability to hopefully get at composition and mineralogic variations using the color data. So we do that a lot with the cameras. We have the RGB filters plus 11 different colors in Mastcam-Z. And first thing we did was look at our cal targets and convince ourselves that the cal targets, when calibrated, look like what they looked like in the laboratory with our cal target and the SuperCam cal target. And a lot of this was discussed at LPSC. So I point you to those presentations. And then we started pulling out some of our first spectra. And we've taken a couple of dozen sequences like this now early in the mission, looking at the different RGB classes, but extending those color variations out to the shortwave near infrared, just beyond 1 micron. So we have a little bit of sensitivity out there to different kinds of iron oxides, different kinds of iron-bearing silicates like olivine and pyroxene. These are cameras, they're not spectrometers, right? So we can't do true mineralogic characterization like you might be able to do with a high resolution near IR spectrometer, or of course an XRD, something like that. We don't have those capabilities. But again, we can use these capabilities to triage the different kinds of classes of multispectral and near infrared rock materials and regolith materials that we see. SuperCam has a near infrared spectrometer that picks up at the longest wavelengths and goes out to about 2.5 microns. So it really substantially augments and enhances what we can do with Mastcam-Z, but just for individual points. So they can do little rasters of points, but they can't get the full context. So again, we can help guide the best choice of where to apply those little point rasters to get as much as we can out of the composition. So our calibration is looking good. We see spectral diversity. Excuse me, that's a good sign. We see some evidence of weak features that are probably consistent with iron oxides, iron 3+ oxides. Not surprising, and some of these, of course, have been detected from orbit for some time all over the planet, but also iron-bearing silicates like pyroxene, like olivine in some of the regolith materials. And so we're able to make the connection on the ground with the same kinds of spectral units seen by CRISM and other orbital remote sensing instruments. So that has been really important. We're able to verify that in fact we do see olivine and pyroxene on the ground that's interpreted from orbit, and extend the mapping from that tens of meter scale at CRISM down to the millimeter to centimeter scale with instruments like Mastcam-Z, and then extend it further, hopefully with the Raman and other capabilities that'll come online with the arm-mounted instruments. So that's pretty exciting to be able to do that. And we're hoping to be able to write this up, and when we're happy with the calibration, get it out there into the community. Of course, we'll be archiving all of those images in the PDS. First archive delivery, I think, is scheduled for August. So that's actually coming up pretty soon. So let me end here, talk a little bit about what's next. I mentioned that we're finishing up the SOX period, the transition to surface phase, the instrument calibration, instrument characterization, lots of it done. Still a bunch to do, but lots of it done. Enough done that we're confident in taking and starting our first science campaign. And as reported late last month by our project scientists in a media briefing, we're going to do this campaign that looks something like this red path. Maybe not exactly, but something like it. Going from our current location to the southwest and back again, doing a sort of a walkabout. You know, we find ourselves on this crater, fractured crater floor unit. It is among the oldest units in the crater, as determined from both crater counting and relative age dating with the other geologic units, map units in the crater. It is a unit that does hold craters, so it's a datable cratered surface. Getting samples from a datable cratered surface has been an important goal of the mission since the science definition team outlined what the science goals of such a mission should be back in 2011 and 2012. And we know it's important to the community to get some what are likely basaltic samples. Mars is a basaltic planet. We have every reason to believe that there's basaltic materials here, although they may have been reworked and weathered in some cases. But getting samples of this datable unit is a pretty important part of our mission. You know, it's not the astrobiology part, but it is the basic Mars planetary characterization part and the absolute age dating part that, of course, we're able to do so successfully on the moon. Let's try to start to establish that absolute age dating connection for Mars as well through samples like this. So we think we should be able to, hopefully, if things come online as they're predicted to over the coming months, maybe get 3 or 4 samples of this material from 1 or 2 of these units. There's the unit that we're in, the cratered floor unit. There's the unit that we almost landed in that would have been deadly because of the big sand dunes, which has layering that you can see, some from orbit, some from the surface in the images. And it probably could represent, these could represent layered or laminated mudstones that were part of the original lake floor. They're farther away from the rim. They could represent the remnants of bottom set, deltaic bottom sets. If the delta went out that far, we don't know whether it did, but they could just represent mudstones, fine sandstones and mudstones that are distally deposited from the river systems in the west and the north that deposited sediments from the Noachian highlands. So great potential materials to sample. We think we can get to a small part of that dangerous Satar region that we can't drive in, but we think enough of it might be exposed. We might be able to sample there, follow along, see if we're right. We don't know yet. We're going to try to find out. But this will be our first science campaign, our first sampling campaign, and it's likely to take many hundreds of sols. It's likely to take the entire rest of the calendar year at least. We don't know exactly how long, but that seems likely. And part of it is because this is, of course, the first time we're checking out the whole sample system, sample collection, sample documentation, the coring process, the process of getting the cores into the rover, doing the automated processing with the tiny robotic arm inside the front of the rover that moves the sample around from station to station, hermetically seals it and stores it. All of that is going to get, is being tested out at the component level during this first 100 days, but at a very high level, it's never, of course, actually been done with a real sample. And so that is going to be part of this science campaign, testing out, proving out that entire process. So that's pretty exciting. So, but that's probably going to take us the rest of the year to get to that point and collect those samples, which are going to be important for the community. And then finally, we will chart a course for the Delta. We'll get a bunch of information going to the southwest about possibly passing through this dangerous area. Down here, we'll get a whole bunch of high resolution imaging data and topographic information. Maybe there will be a pathway through here. Maybe we'll have to go up and around in a more counterclockwise direction around that terrain. We can get around it either way. It's just, you know, it's assessing how long it takes to decide which path to take. And there's good reasons to go both directions. It's going to be a little bit of a knockdown, drag out brawl, but friendly and collegial. We have a great team. That decision doesn't need to be imminently made, but we will be collecting a lot of data on this walkabout to ultimately make that decision to get to the Delta. So that will be then coming up sometime in 2022. So that's going to be pretty exciting. Lots of ways to follow along. We're super excited about having the community and the public follow along during this early phase of the mission, eventually getting access to the data through the PDS once we, you know, figure out all the calibrations and all that kind of stuff. That first release will be coming out this summer at 6 months after landing. There's these research papers in Space Science Reviews that describe all the gory details of the instruments, the calibration planning, and the mission operations planning, the sample caching system, all that in this great collection of papers. Those traverse path maps I pointed out. We release the raw images to the public every day from all the rover cameras, and lots of people are following along. That's been great. We've got a public website for Mastcam-Z where we put calibrated images out there in PNG format. When we do the live fielding and stuff like that for the amateurs and others who want to work with the data. That way, we put mosaics together. We've got a great blog and all kinds of, you know, insider information approved for release to the public that we share on that site. So check that out for some of the latest. And then, of course, the JPL and NASA have just amazing resources for news, for multimedia, social media. Hopefully you're following along if you're a social media person on Twitter and Facebook, all that kind of stuff. So lots of ways to keep up with the mission. And we know we've got lots of fans out there, especially teachers and students following both Perseverance and Curiosity and Insight, and now trying to keep up with what the Chinese are doing. And, you know, there's just lots of stuff going on. It's a great time in Mars exploration. So we're just about to enter our first science campaign. We are go for science. We've had an amazing first part of our mission. We've got lots of puzzles. We do not have many answers. That's kind of part of the fun of it. But we'll all hopefully discover together what's going on in this place, where are the best places for us to collect those samples that hopefully many of you will be playing with in some of your own laboratories in a decade or so. That'd be great. And please invite me to your lab. I would love to see some of these samples with my own eyes, please. Thanks. That's it. Thank you so much. Appreciate again the invitation.
Thanks so much, Jim. I really appreciate that. Those are some really fantastic images of the rover, both images and sounds of the rover in flight. That really drives it home. Sometimes a little hard to get the sense of applause or appreciation through the Zoom seminars. So if you want, you can use the chat to express your appreciation for Dr.
Thanks.
Thanks. Let's go ahead. If you have questions, please go ahead and enter them into the chat. So it looks like during the talk we had a comment from Megan Russell, who said that the recordings of the sound reminds of the wind recordings on board one of the Venera landers on Venus, which is definitely true. We also had a question from Robert Balchels. I apologize if I mispronounce any of your names, but it said, it looks like the most direct route towards the Delta front is through the rough terrain that was avoided during the landing. Do you have any idea right now which route you would take?
Yeah, that would be the way the crow flies, right? But we can't do it. The rover drivers that we work with are, I mean, unless we discover some really narrow path as we skirt along the boundary of it, I guess don't ever say can't, right? Never say never. But unless we discover some path that we're not seeing right now. And a lot of this just comes from orbit. The high-rise data show us that surface in great detail, and we can expand on that from the ground with Mastcam-Z and the Navcams. There's not an obvious way through it that's close to where we are now. That we have to either go somewhat southwest or somewhat northeast to get to places that we can start to go around it. And there's good reasons to go both directions. You know, we need the time to complete the characterization of the system. We want to sample this crater bearing unit anyway. So I think it's all going to work out just fine, that we don't actually need to take the beeline path to the delta.
John Littleton asks, one of the early images of the Perseverance landing site appeared to show a mosaic of smaller images assembled to display a panorama image. Can you talk a little bit about the process used by the imaging teams in assembling a panorama image from smaller images?
Yeah, so the Navcams and the Mastcam-Z is up on the mast, that we use the mast motion to point the centers of the field of view at the right spacing, depending upon, you know, the Navcams are very wide angles. It only takes, you know, like half a dozen images to go all the way around. But the Mastcam-Z could take, you know, 20-something images at our widest angle, or, you know, many dozens of images, 40 to 50 images at our very narrowest angle to go all the way around. So we've used a variety of methods depending on how much time we have. Sometimes we have enough time to, we have to zigzag back and forth. One of the early mosaics, we just went all the way around, but just one tier, like along the horizon. We try to match the lighting from day to day, but you can't always do that, because sometimes you're at the mercy of when the communication pass orbiters are coming over, and so you can't observe at a certain time that you would want to, but you also don't want to say, no, we don't want to observe it all today, you know. So we try to match up in time, and it's actually kind of remarkable how this big mosaic that's coming out next week is relatively seamless, even though it spans a big range of time of day. If you look closely, you can see there's some rocks with their shadows on the left and some with their shadows on the right, because there's taken in the morning versus the afternoon. And so there are those kinds of effects you just can't get around. But we just don't ever have the luxury of the time to take an entire panorama on one day with the high resolution cameras. We can do it with the low resolution cameras, not with the high resolution. Then we bring them into software. We have a model. Each camera has a model, and that information's in the header to each image. It'll be in the PDS labels for folks who want to use their own homegrown software. I know the amateurs who work with the images bring them down and you throw them into Photoshop or something. There's like these automated tools now that can build panoramas just by, I don't know how it knows, it's just pattern matching, I guess. And sometimes it gets them dramatically wrong, but they look good. So you have to be a little careful with those things. But I know there's a lot of folks just working with the raw data, making mosaics using their own tools or freeware or tools like Photoshop.
Great. So Milan Krupa has a question. How does the regolith compare to lunar MTL? So
as best we can tell, we're looking at a sandy, probably olivine sandy bearing regolith based on orbital data from CRISM and what limited amount of information we have on the mineralogy to date from tools like Mastcam-Z. Pretty sandy, pretty low dust actually, compared to Gusev, where the Spirit rover landed, compared to Gale, where Curiosity is. Those are much more dusty sites. But probably this site is more dusty than Meridiani, where the Opportunity rover landed. Those are even darker sandy deposits there. So probably not as fine-grained as much of the lunar regolith. We see more evidence of grains, cobbles, pebbles in this particular regolith here, as we have at the other landing sites and rover sites. So it's sort of, except for the dust abundance, there's a lot of similarities in the regolith that we see here with the other places we've been on Mars. not surprising, right? There's, there's a global component of the regolith on Mars, globally distributed sand and dust. Of course, the dust is always globally distributed through dust devils and major dust storms. And the sand, much more slowly, also appears to be pretty homogenized globally, based on what we can tell from orbit and the lander sites. I guess the only other thing I'd add is there's a local component to regolith everywhere. We see evidence of some of these rocks. You can see it in the images. Some of these rocks are weathering in place mechanically, producing relatively coarse-grained regolith nearby. There's evidence in some of the delta deposits for mechanical breakdown of some of those layers. And of course, you see the scree slopes, the fine-grained scree slopes, which appear to be, obviously, that's material that came from that coarser-grained, outcroppy sedimentary layers. So not a lot of sedimentology on the moon, except for some lava flow sedimentology. So that's a little bit different. But otherwise, there's definitely some similarities in the fine-grained components.
So speaking of dust, Bob has the question: how do you clear dust from the lenses?
Yeah, we don't. The experience gained from previous missions is that when you're not using the cameras, point them down, so we're not just collecting dust that's always falling out of the atmosphere. And then when we're using the cameras, just use them, and then when you're done, point them down. They do get dusty. For those of you who wear glasses, I wear glasses a lot too. Your glasses can get pretty dusty and dirty and not really have much of an effect on your vision. That stuff is so far out of focus. It's dimming the scene ever so slightly, but not introducing big blobs of hairs or dust specks in your vision because it's so far out of focus. This is the camera lens. We really expect there to be some dust adhering to the lenses. And the past experience is that Mars cleans it off occasionally. Dust devils are very active at Jezero. We see them in a lot of the images that we've taken, and some of the helicopter videos have some amazing dust devil action going on. You can check out a blog by Mark Lemon at the Mastcam-Z website about that. And some of those dust devils are going to pass over the vehicle as well. And they cleaned off the solar panels occasionally on Spirit and Opportunity. They cleaned off the cameras on Spirit, Opportunity, Insight, and Curiosity occasionally. We expect that to happen as well. So we decided not to take any heroic measures to put little wipers or something on it, which would have cost some other, trade for something else in terms of resources, and just live with the fact that they're going to get a little dusty and it won't be so bad.
Great. Kumar Babaglu, and I again apologize if I mispronounce anybody's name, it says, thanks for the excellent talk. Could you explain how the delta could be older than the crater?
Not older than the crater, older than the crater floor. Certainly not older than the crater. It's much younger than the crater. It's a Noachian crater that goes back to very early in the history of Mars. The question is, has there been subsequent deposition, maybe extrusive volcanism, maybe pyroclastic volcanism after the delta was in place, or was that before the delta was in place and the delta is the youngest? So the crater floor material is younger, we believe, than the crater itself. There has been subsequent deposition since the original cratering event.
Great. Siddhartha Pandey asks, so the Lonar crater in India is one of the few basalt craters on Earth with a delta fan, smaller, only 2 kilometers wide, and has several features that could store ancient biosignatures. What are some important ways we could utilize such sites to support ongoing and future Mars exploration?
Yeah, I mean, that's a great example of many kinds of analog sites around the world. A number of people on our team and many people in the Mars community, the planetary community in general, and heavily involved in analog studies. I was involved on a number of them when I was a grad student working with Dick Morris and others at JSC in Hawaii. We were looking at palagonitization and formation of iron oxides from basaltic precursors, right? So Lunar is a great example. There's lots of other craters around the Earth that are great examples, other basaltic environments that are great examples. And especially when you can combine environments that are more Mars-like, maybe more basaltic, with those that show clear evidence of sedimentation and fluvial activity, lacustrine activity, places like deltas that can preserve sediments very well because they're low energy, fine grained deposition environments. So there's a number of folks around the world who are doing exactly such analog studies. You write them up and you identify potential biosignatures. Maybe they're morphologic, maybe they're textural, maybe they're chemical or mineralogic, organic, and try to tie those biosignatures to specific kinds of observations that could detect such biosignatures with a much more limited set of science instruments that we can bring to a place like Mars than we have available to us on the Earth. So that's often the really challenging step. Yes, of course, you just take this and do, these detailed GCMS blah, 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 blah on them. And of course, that's how you get the answer. We do rubidium strontium on it, whatever. And we can't do that, right? Out on Mars or other places. Or if we can do it, we certainly can't do it to the fidelity that can be done in the best laboratories on the Earth. So that's an important step in analog studies. What can we learn from these places that we can translate into a measurement that you can make with an asset that is out there and its capabilities and limitations?
Great. Quick follow-up question from Milan Krupa again about the regolith. Is the regolith electrically charged as it is on the moon?
Well, that's a good question. I'm not sure if we have a direct way of measuring that, but it certainly sticks to the wheels. And it has stuck to plenty of rover wheels in the past and solar panels. And I guess there's every expectation that this extremely fine-grained smoke-sized dust material that's being moved around and abrading the surface is going to electrostatically charge. And I know there were some triboelectric studies that were done as part of the MER solar panel studies and others. So there's every expectation that yes, it is electrically charged. Now, I don't know of any reports of Mars lightning from any of the orbiters going over the night side. Don't know about that. Maybe somebody can correct me. But we certainly see evidence of dust in places that we've sent rovers and landers adhering electrostatically to the surfaces that are in contact with the dust.
Okay. And we have time for one final question. This one's from Dave Wilhelm. What improvements and challenges do you see for imaging on the recovery rover for ground sample tubes when it arrives on Mars circa 2026?
Yeah, that's a great question. I have no idea if that little fetch rover will carry science instruments or be allowed to carry science instruments. It has to have cameras that at least let it find the samples, that at least can follow the tracks and go to the right place. But to do that doesn't have to have cameras with the capabilities of a Mastcam-Z like system. Could do that with hazard cameras and navigation cameras, just engineering cameras at much lower fidelity. So, is there going to be the capability to put science instruments on that vehicle? I certainly hope so. And I certainly hope that, since we're going back to the same place, that if we do have the ability to send science instruments, that they can be very complementary to what Perseverance is carrying. Certain kinds of either imaging or spectroscopy that complements the measurements that we have from Perseverance. And maybe, by then helps answer the questions that we ultimately can't answer with that payload at that site. But that right now, that's wishful thinking. The whole thing is kind of science fiction right now. We don't know really how it's going to unfold and what it's going to be. But certainly my hope is that we'll be able to do some unique new science from the ground with that rover and from orbit with the orbital assets as part of that program too.
Awesome. Well, I believe we're out of time, but thank you so much for this talk, Dr. Bell. This was really, really great. And really looking forward to what you can do with once the science operations really kick into it.
Stay tuned. We'll try to share everything we can.
Awesome.
And thank you again for the invitation, and thanks everybody for participating.
It's been really great.
Thank you, Project.
I also wanted to say thank you. I'm sure there were many muted oohs and ahs as we were looking at the images and the videos.
Yes.
Well, I know you laughed at my jokes at least. Maybe nobody else.
All right.
Okay.
All right. Take care.
All right. Thanks, everybody.
Thank you.
Bye.
Thanks for joining us for the LPI virtual seminar. There will be no seminar speaker next week, the 3rd of June. However, the following 10th of June, our guest will be Dr. Scott Sanford of Ames. We'll be talking about the Stardust mission. Thank you very much. Have an excellent afternoon, evening, everyone.